Hi, it's Dr. J here. Today I will explain what the photoelectric effect is, how light frequency and intensity affects the photocurrent produced, and how an applied voltage affects the photocurrent. So the photoelectric effect is where light or electromagnetic radiation shines on a metal and then electrons from the metal gain enough energy to be released. So you can see in this diagram, here is our metal, which is the rectangular box. We have our metal surface. We have our light coming in, and the light's energy is HF. The light comes in, collides with an electron. So you can think of these as photons colliding with the electron. The electron gains enough energy to get to the surface and then is released. So the electrons that are released are known as photoelectrons. And these here we call light or we call photons. Generally speaking, we say that the more intense the light is, then the more photons that we have. The other point about photons is that they transfer all of their energy to the electron that they collide with. Okay, so let's explain this diagram and use an equation. Some of the energy of the light is required to free the electron, and this is called the work function, and this is represented by this green arrow here. The remainder of the energy that the photon has given to the electron is imparted or observed as kinetic energy. And so that photoelectron leaves the surface with kinetic energy, and we show that as being a blue arrow. So we can write that the energy of the light is equal to the work function plus EK. So E light equals work function plus EK. Not all light can cause a photoelectron to be released. It needs to have enough energy to release the electron. That minimum energy is related to something called the work function, and the work function is specific to a metal. So the work function is equal to H times F naught, where F naught is the minimum frequency of light required to cause electrons to be released. This is also called the critical frequency. So it means that the higher the frequency of light above F naught, then the greater the kinetic energy that the photoelectron takes away with it. So EK is the maximum energy, kinetic energy, that the photoelectron can have. So a common setup that we use to study the photoelectric effect is that we see here. So what we have is a variable voltage here. So this can be positive or negative. We have an ammeter to measure the current. So we've got light coming in, hits the metal surface, photoelectrons are released, they are detected and measured by the ammeter, and this is our variable voltage. Okay, so if we apply a negative voltage, this detector will be negative and will repel these electrons here. If you make this plate negative enough, then the electrons can't actually reach the plate and therefore no photocurrent will be detected. Okay, so more about this in a moment. So if the voltage matches the maximum kinetic energy of a photoelectron, then no photocurrent can flow. So let's have a look at this graph here. So this is a graph showing the photocurrent that results from varying the voltage. So that's the voltage that we're talking about just here. So there are three sections to the graph. So we have the maximum photocurrent at the top here. And this is when our electrons are flowing freely to the detector. It doesn't matter how much more negative I make the voltage here, sorry, positive I make the voltage here, that's the maximum current that can flow. Now, as we have if we look at the graph, we can see that this photocurrent does decrease down in this section here. So as the voltage becomes less positive, so the voltage is less positive here. Fewer electrons are going to make it to the detector, resulting in a lower current. Remember that EK is the maximum energy that the photoelectron can have. Some will have less, and so smaller voltages will stop these. So at this point here, so we've got our negative voltage over here in this section here. So this is positive voltage, this is negative voltage. So that negative voltage, remember, is acting as a repelling or a decelerating force to those electrons. There will come a point at which no photoelectrons can make it to this detector here, and that's because the maximum kinetic energy of those photoelectrons has been matched by the voltage that we've applied just here. Okay, so we then have a look at a graph showing the photocurrent that results from varying the frequency of light. So here I've got high frequency, which is our blue, going to a lower frequency green, going to a lower frequency red. Okay, so what we can see here is that as the frequency decreases, the stopping potential decreases. So the higher the frequency of light, the more kinetic energy the photoelectrons will have, therefore the higher the stopping potential will be before we can actually stop those photoelectrons. So as frequency increases, so does the kinetic energy of the photoelectrons, so the stopping potential will increase. The maximum photocurrent for a given metal and light intensity is the same for all frequencies of light. So see how it maxes out just here. The intensity of light will increase the number of photons that are available to release electrons, and therefore then you would have a maximum photocurrent. So this is a situation where we've got the same intensity, so therefore you're going to have the same maximum photocurrent. Here is another graph showing how the kinetic energy of a metal varies with the frequency of light. So let's just take a simple, just the single metal here. So from plotting this, the increasing frequency with kinetic energy. So what we can ascertain from the graph, because remember our equation is E light is equal to the work function plus the kinetic energy. Let's rearrange that so the kinetic energy is equal to the frequency of light, take away the work function. So there's our kinetic energy on the y-axis, so that's EK. Then I've got frequency, which is on the x-axis. So therefore, the slope of the line has got to be h, and the y-intercept is going to be this phi value here, which is our work function. So when you're given kinetic energy versus frequency for a substance, you can work out the work function, and you can also work out the critical frequency, so the frequency required before a photoelectron can be released. So the work function can be found from the y-intercept. The critical frequency to produce a photocurrent can be found from the x-intercept. The EK of the electrons increases as the frequency of light increases. Note also that for any metal, the lines will be parallel because they all have the slope of Planck's constant. Okay, in this video, we explained the photoelectric effect. We talked about the effect of applied voltage on photocurrent. We talked about the effect of light frequency on photocurrent. And we also looked at the effect of frequency on the kinetic energy of the photoelectrons. So thanks so much for watching my video. In my next video, we will work through the 2021 WACE question related to the photoelectric effect. Remember to subscribe to Dr. J's channel for the latest physics tutorial.